let's think about why our maximum velocity should be 78 centimeters per second in terms of the reference circle model. If we have a pendulum swinging 30 centimeters from one side of equilibrium to 30 centimeters to the other, we'd better have a reference circle whose radius is equal to that amplitude, 30 centimeters. If we're moving around a 30 centimeter circle at 2.6 radians per second, then our reference point on the circle is going to be moving at velocity, which is omega times r, which is 78 centimeters per second. Remember, each radian here corresponds to 30 centimeters along the rim, so 2.6 radians will be 78 centimeters, and 2.6 radians per second will be 78 centimeters per second. So at any position here, the velocity is, or the speed of this reference point around the circle is 78 centimeters per second. Now, as the reference point moves around the circle, the vertical projection line moves back and forth like this, as we've seen from the simple harmonic motion model on the computer, from the reference circle model. We have this kind of motion. When the velocity, or when the reference point is here, the velocity of the projection line, the velocity of this pen if we're following the reference point, will have to be less than the 78 centimeters per second, because 78 centimeters per second is off in this direction. And we're following just one component, the x component of this velocity. So our velocity will just be the x component of this velocity vector at every point. Now, when the velocity vector is at the top or the bottom, that x component is just equal to the whole velocity vector. So we get the whole 78 centimeters per second as the x component of the velocity. So when we pass through this point, we'll be moving at the 78 centimeters per second. When our vertical projection line comes back and passes through this point, it'll also be moving at 78 centimeters per second, because it's moving at that instant parallel to this point, which is moving at 78 centimeters per second. We can also look at the acceleration situation. Now, we noticed on the original that our acceleration function was negative omega squared a cosine omega t. This gives us a maximum acceleration of omega squared a when the cosine of omega t is negative 1. So the maximum acceleration is omega squared a. What does that have to do with the reference circle model? Well, if we're moving around the reference circle at angular velocity omega, radius a, at a point when theta equals omega t, our velocity here is going to be omega times a, just the angular velocity times the radius of the circle. That's something we should know pretty well by now. What's that do to the acceleration? Well, at this instant, velocity equals omega a, and the acceleration is back toward the center of the circle, a centripetal acceleration whose magnitude is v squared over r. What's v? Well, v is r omega a. So if we divide omega a squared by the radius, which is a, we get omega squared a. So that the acceleration at every point on this reference circle is omega squared a. Now, if we're moving back and forth again, we're going to be matching the position of this point. At this point, the acceleration of the point is in this direction, and the component of that acceleration in our direction of motion is a component in the x direction, and it's not equal to the whole omega squared a. It's not equal to the entire quantity omega squared a. If we're at this point or this point, however, the acceleration will be toward the center and will be parallel to the x-axis. So when we're here, we're getting the entire omega squared a acceleration, and when we're here, we're getting the entire omega squared a acceleration. So that our maximum acceleration, omega squared a, will equal the centripetal acceleration of the point on the reference circle at this point and at this point. Now, coming back to this picture, when theta equals omega t, our velocity is omega a. The velocity vector is perpendicular to the radial vector here. so that the angle of the velocity vector is going to be omega t with respect to the y-axis, since the radial vector has angle omega t with respect to the x, and these two vectors are perpendicular. This means that the x component of our velocity vector, if you do a little trigonometry here, you see, has to be negative the sine of omega t, the sine of this angle up here, times the velocity. The velocity is just omega a, so we see that the velocity function has to be negative omega a sine omega t. So the reference circle model, if we accept it, gives us the same result as the calculus for the x velocity here. And this would be the velocity of the pendulum that we're modeling with this system. Similarly, over here, our acceleration vector is back toward the center. So if our position here is omega t, then our angle here will be omega t, but that'll be with the negative x-axis. Our acceleration component in the x direction is then going to be negative omega squared a times the cosine of omega t. If you just look at the triangles, the trigonometry of the situation, this green vector ought to be a little bit longer. I didn't quite draw it long enough. But just by analyzing this vector and getting its x component, we see that it has to be this, and that this agrees with what calculus told us about the acceleration of a simple harmonic oscillator.